Welcome to our last part of Lecture 2H. We're going to take a little bit deeper dive into colligative properties here. So our last colligative property that we need to talk about is osmotic pressure, which we denote by a Greek letter pi, the capital pi. So what is osmosis? Well, it's a movement of solvent molecules through a semi-permeable membrane. And we see that in the diagram here, where you have a pure solvent. Change out my color. We have pure solvent here. We have some type of solution in here. And so the osmotic pressure is caused by solvent molecules moving into the membrane. And as we'll see in the diagram in just a moment, what happens inside is your solute particles in that solution are too big to move outwards. So what you have between the pure solvent and the solution inside is you have a concentration gradient. You have a difference in concentration, and this is what drives these two things to try to be equal. And if solute particles can't go out of the semi-permeable membrane to increase the concentration of solute, and here, the other way that this can happen, what has to happen to make these two things equal is that pure solvent molecules are going into the solution to try to dilute it to the same level as what's out here. But of course, since this is a solution and this is pure, if no solute particles go into that pure solution, there's no possible way to dilute a solution to become a pure solvent. So there's always a constant drive that wants to push solvent molecules into the solution through that semi-permeable membrane. What that does is it causes pressure inside that membrane, and we can see here that we've got a column of fluid up there working against atmospheric pressure. Now, the other thing you've got is you've got atmospheric pressure pushing down, but you've also got gravity pulling down here. And so eventually those two things balance out. And the height of that solution column between the top of the solution and the top of the meniscus inside the tube is how we measure the osmotic pressure. Migration will continue of solvent particles in. It'll go in and out constantly, but you get a net migration in until the pressure to the solution from the solvent is equal to the pressure out, the atmospheric pressure. So this is what we call the osmotic pressure value. So here's the diagram I was mentioning. So you can get a couple of different things happening. If you have a solution made up of large molecules like we've got right here, or we've got some hydrated ions here, this would be a negatively charged ion. They didn't put a little sign on there. That would be a negatively charged ion. So an anion, we've got a cation up in here with a positive charge. You can see here that your large molecule, maybe it's a protein, maybe it's just a large sugar or something, can't pass through the semi-permeable membrane. The pores in the membrane are just not big enough. Now you might say, how can some of these ions not pass through? They should be smaller than a water molecule. Well, they might be, but remember that when positively or negatively charged ions go into solution, they are going to form these ion dipole interactions with these ions, and so they move as a big hydrated ion here, and they actually tend to move as a larger conglomerate particle than even a molecule. So they also find it very difficult to pass through those membranes, and generally don't. So if we look at the equation for osmotic pressure, very similar to the ideal gas law. Here we see for the ideal gas law, we normally think of it as PV is equal to nRT. If we divide both sides by volume, it just moves the V over to here. So you have nRT over V. We can separate out that N over V there, and that gives us a moles over a volume. And we know that moles over volume is a concentration. And so we can put something very similar to osmotic pressure here. So rather than P, we have pi. Osmotic pressure is equal to C, concentration in molarity, and this is of the solution that is inside that semi-permeable membrane times RT. And just some applications of osmotic pressure. You may or may not have heard of the process called reverse osmosis. So this is where we force water out of the concentrated solution through the semi-permeable membrane and into where the pure water is. Now, that's not the direction that the water wants to go. The direction water wants to go is this way, because it wants to try to dilute that solution there. So what we have in this diagram is fresh water over here and seawater over here. So if the ions cannot pass through this way, then the water is trying to dilute the seawater to get to the same concentration as the fresh water, which obviously it can't do. So how do you drive then water to go that way? Well, if you want a process to go opposite the way nature wants to do it, you've got to apply work, and that's what this pressure is here. So you would have some sort of mechanical device that creates that pressure and forces the solution back through that semi-permeable membrane. The only thing that can pass through the membrane is water, and so you get fresh water out on the other side, and then you get a very concentrated broth flowing out through the bottom there. There's some biological applications to osmotic pressure based on what's hydration in the blood or what's going on in the blood cells. You can get hypertonicity. These are conditions that can exist in the bloodstream where you've got water flowing out of the cells to dilute whatever is in the serum, and the cells just kind of squish out and become flatter. If they're isotonic, that means they're in balance with the sera that the platelets are in the blood cells. And so you've got water going in, water going out at the same pace. Those are very healthy blood cells. Or you can go hypertonic, where you've got something going on in the blood cell itself, and water is coming out of the serum into the blood cell and forcing it to bloat, and as we can see here, even possibly burst, which is not a good thing. And just kind of an example of this, we see an egg right here. It's getting its shell dissolved off in vinegar, acetic acid. And here we have the shell with its egg removed. It's being placed in pure water. And in pure water, the egg inside has a lot of proteins, a lot of things. So the water is going to try to dilute that. And so water is going to be entering through that semi-permeable membrane that was left when the shell was removed, and the egg expands, the membrane expands. Or in this last picture here, it's put into a very concentrated sugar solution. There's probably virtually no sugar inside the egg, and so its water starts coming out of the egg and into the sugar solution to try to dilute it and make those concentrations the same. And so the egg just atrophies and becomes very small as it shrinks. Now, up to now, all the calculations we did in the previous lecture for our colligative properties is we used a molecular solute. We used glucose. And so when you dissolve 1 mole of glucose, you will get 1 mole of glucose particles because the glucose molecule does not break apart. We have learned in previous course that when you dissolve an ionic salt into solution, they break apart into their anions and cations. And so you get multiple particles in solution. So as an example, for something like sodium chloride, your sodium chloride crystal break up into sodium ions and chloride ions. And so if I put a mole of sodium chloride in, I get 1 mole of sodium ions and 1 mole of chloride ions. And in the end, that gives me 2 moles of particles total in solution. And so we have to keep that in mind anytime we're using an ionic salt, because ionic salts break up into several different particles, and you have to make sure that you keep track of the number of particles that it will break up into. So you have to know what your ions are for an ionic salt. Now, we mentioned our colligative properties depend on number of dissolved particles, and so you've got to account for all of those particles. We are going to adjust our equations accordingly so that when we have ionic solutions, we keep that in mind with the calculation of the molality, because really what we want to do is have the molality of particles, not necessarily the molality of a particular entity. So what that leaves us with is something called the Van Hoff factor. And the Van Hoff factor is just an I And we see here all our equations are adjusted by nothing more than placing an I here. Now, I is approximately equal to the number of particles that form, but it does vary with concentration. As things get more concentrated, the particles can stick back together, and so you start forming these little conglomerates, and the actual I value is usually a little bit less than what you might expect. So if you have a fairly concentrated sodium chloride solution, perhaps your I value may not be 2. It may be as low as like 1.7 or 1.6, simply because you have some sodium chloride clusters forming inside of that solution, and all of the ions are not necessarily separated from each other. So the theoretical value of I is always the number of ions formed. So for sodium chloride, the theoretical value of I would be 2, because you should get 2 ions formed for every mole that goes in. That is what we will use for our problems in the course. We're not going to worry about the actual numbers unless it's something that we're trying to calculate. So I might have you calculate a theoretical value or an actual value of I based on the colligative property measurement. Now, we can also use a colligative property to calculate molar mass. It's actually one of its more common uses in an industry such as biological industry. If you're making new proteins or new sugars or polymers, you can use the colligative measurements in order to find the molar mass of these really large molecules. And when we say large molar mass, some of these things for polymers can get up into the tens or even hundreds of thousands of grams per mole. And trying to calculate that is virtually impossible just by normal methods. And so colligative properties become a really useful way of doing this. So natural or synthetic polymers, especially natural polymers, if something new is found, gives them a way of finding the molar mass. Biopolymers, such as make synthetic skin or something like that, it works really well with also. And we're not going to do an example, but we'll just kind of talk about it here. If we know the number of grams of material that we put into a solution, do a colligative property measurement on it, and that can take us back to what the molality must be. And if we know what the molality must be, and we know the grams that went in, we can back that calculation out to molar mass.